So the periodic table after tonight, hopefully, and again, this is where you're gonna need your periodic tables. Grab your periodic tables. We're gonna be marking them up all crazy, doing some Aufbau stuff with them. It's gonna get nuts. Um, hopefully, after tonight, you will understand why the periodic table is shaped the way it is. Brief background on the periodic table: the idea to organize the elements based on a repeating pattern uh, was developed by this man right here, a Russian scientist, Dmitry Mendeleev. He was a chemistry professor in Russia, and he wanted to make some more money, so he thought, well, I'll try to write a book. And at the time, if you were taking chemistry, in the early 1800s, they had discovered maybe like 50, 60 elements, and there was no rhyme or reason to it. You just would go in and they would talk about, hydrogen one day and gold the next day, and like, copper the next day, and there was no rhyme or reason to it. So Mendeleev, because he was writing this book, wanted to come with a way to kind of organize everything. And he, essentially happened upon, after a lot of work with this, he happened upon this way to organize the elements, periodic table of the elements. His table went up by increasing atomic mass. So the little numbers at the bottom, and if you're looking at your periodic table, that's not a very big deal. You got to remember that they don't discover the proton until Rutherford's experiment, which is, early 1900s. So they haven't discovered the proton. So atomic number doesn't exist when Mendelev's doing this. The atomic number when Mendelev's doing his periodic table was literally just it's where it came on the periodic table. It didn't mean protons. So they didn't have the atomic numbers. They didn't know about protons. What they did have was the molecular weights, the molar masses of the elements. And Mendeleev arranged the elements based on the increasing molecular weights. And if you look, as you go from left to right, the weights pretty much do always increase. There's only a couple exceptions. Nickel is actually a little lighter than cobalt, so element 28 and 27. On Mendeleev's periodic table, he had cobalt and nickel flipped. And there's not too many other ones that would be flipped if you kind of look around, and some of those elements hadn't even been discovered. Mendeleev is the rare example of a scientist whose work gained wide acceptance while he was still alive. Usually, if you have some groundbreaking idea, it's not till after you're dead that they're like, "Oh man, that guy was onto something," But Mendeleev, his periodic table within like 4 or 5 years was just widely used. A couple reasons for that. One, it worked awesome. And two, when Mendeleev was building his periodic table, he left some holes on it where he said, hey, I think that there's an element out there that we haven't discovered yet that belongs here. And he took it a step further. He said, I think it should have a density of this and a melting point of this, and it should have these properties. And then people discovered it, and it had those properties, and they were like, all right, that's weird. This guy must really be onto something. So good for him. The modern periodic table, not developed until Henry Moseley, who died in World War I at 27. So you can imagine, the actual modern periodic table hasn't been around super duper long, only a little over 100 years. Okay, so where are we? Well, after Bohr's work, which we just studied, and we will do his lab tomorrow night. It is exciting. What is going on here? Here we go. After Bohr's experiment, we believe there is a nucleus, and then we believe that electrons, wow, I cannot use this mouse. Electrons circle the nucleus in these spherical orbitals, right? Okay, that's where we're at. That's the planetary model of the atom. Unfortunately, folks, there is one more to go. There is one more improvement that can be made, and this one is made by another pop culture icon, Erwin Schrödinger. You've probably heard of Schrödinger from Schrödinger's cat, where a cat can be simultaneously alive and dead at the same time. That actually comes right out of the double slit experiment. We won't have time to get into that, but same guy, same stuff, same quantum mechanics stuff. Anyway, Erwin Schrödinger, who is really a wonderful mathematician in statistics, he thought he would try to tackle the atomic model and what was going on to try and describe the behavior of electrons. And what he discovered is that the electron orbitals are more complex than just spheres. Some of the orbitals are indeed spheres, but then other ones are more complicated. There are these dumbbell shapes and stuff. And that's really Schrodinger's major contribution. Schrödinger comes up with this Aufbau theory. Aufbau theory. Aufbau is German for to build. So Schrodinger's theory literally tells you how to build the electron cloud of the atom. And the new thing in this is that orbitals are not all spheres. They have 3 additional shapes, which is what we're going to talk about right now. So the spheres. Some orbitals are indeed spheres. Schrödinger calls these S-type orbitals. But then they get more complex. So you can see, so here's the spherical orbital. That's the first spherical orbital. Here's the second spherical orbital. It's just a bit bigger. And then you can see the orbitals start to come as sets. So this is a set of 3 of the next orbitals. These are called dumbbell-shaped orbitals. Then the next shape of orbital comes like this in a set of 5 orbitals. 4 of them look like X's. 1 of them looks like one of these dumbbells with a donut around it. Those are called the D-type orbitals. And then there is a 4th shape, which I think I have a picture of somewhere in here. No, no picture. Come on. There they are. This is the 4th shape of the orbital. These are called F-type orbitals. They come as a set of 7 orbitals. So how does Schrödinger figure all this stuff out? He figures all this stuff out with a heck of a lot of math, folks, which we will get into. Stay calm. Okay. Now, when you were in high school, chances are they probably had you, if you did this at all, they probably had you memorize this silly pattern. Okay. Where you get the 1s and the 2s, and where you take like, and you kind of like go down through these things, like you cross them off as you go. I guess you go this way. Yeah, you go this way. But anyway, maybe some of you remember doing that. I am not a fan of that. I don't like memorizing stuff. I actually, the way I teach it, I teach people how to use the periodic table to figure all this stuff out, which is what I'm going to show you right now. So I'm going to get my projector hooked up here. I got a projector here. I got another computer to project a periodic table up here. It's going to be total madness. I'm going to turn the lights out here eventually. You're going to need your periodic table. And I'm going to show you how to use the periodic table with just a little bit of marking up and a little bit of labeling to figure out all this stuff. We're actually going to write electronic configurations all the way up to barium, and we're going to draw the pictures for atoms all the way up to calcium. So it's pretty cool. Here we go, folks. Periodic table there handy. I am going to fire everything up. Give me a minute. Yup. Hoping that's showing up there all right for you. Here we go. All right. To Aufbau with your periodic table. Maybe a little bit of light. Hang on. Let's try this. Not better. A little bit. Okay. To Aufbau with your periodic table. What we got to do is we got to mark a couple things up to get this thing ready to Aufbau. So what do we need to do? First thing we got to do, we got to move hydrogen. I'm sorry, we got to move helium. We're going to move helium over to here. So helium is going to come next to hydrogen, moving helium over. And then we need to label the blocks, right? So we have S-type orbitals, which are shaped like spheres. We have p-type orbitals, which are shaped like dumbbells. You get a vertical dumbbell, you get a horizontal dumbbell, you get a dumbbell that goes away from you, comes out at you. And then we have the Ds, which are like X's and stuff and all that stuff. So where are these orbitals located on the periodic table? Well, rows 1 and 2, if you do a dotted line between groups 2 and 3, columns 1 and 2, these are our S-type orbitals. That is our S block. I'll try to get that on the white. That is our S block right there. If you do a line down here between groups 12 and 13, okay, over here from group 13, boron's family, to the noble gases, this is our p block. That's where the p-type orbitals live. And then the transition metals, this block in the middle, periods 3, or I'm sorry, column group family 3 to 12, this is going to be our D block. So mark all that off. We got a little bit more marking up to do. See if I can spin this one light around. Let's see, that make it better? Maybe, I don't know. All right. So now we got some more to do. We're going to move lanthanum back up here where it belongs. See this 57 to 71? Move lanthanum back up here. Okay, and we're going to move actinium back up where it belongs. See that 89 to 103? That's where actinium actually belongs. Then down here, folks, are the F block. This is going to be our F block. This is where those super crazy orbitals went. Those are our F-type orbital down here. The beryllium to whatever Lu is, and thorium to lawrencium, those guys. Let me just try to make that a little, yeah. All right, very good, very good, very good. Here we go. So we got our S block, we got our P block, we got our D block, and we got our F block down here. So, as good as she gonna be. Okay, so how do we write electronic configurations? Okay, this is a pattern. If you are paying attention, everyone eventually picks up on this pattern. Okay, everybody eventually gets it. Hang in there. We're going to go slow. We're going to painstakingly go through a bunch of these elements. We're going to talk about things as we go. We're going to draw the pictures. You need lots and lots of paper if you're still old school like me and not writing on a screen. Let's do this thing. We're going to start with hydrogen. So I want to write the electronic configuration of hydrogen. What's the electronic configuration of hydrogen going to be? Oh, I almost forgot. We need to number the rows. So that's row 1, row 2, row 3, row 4, row 5, row 6, and row 7. The rows are going to be the energy levels. Okay, so these are our energy levels till we get to the D's. Then something's going to happen here. But anyway, so I want to write the electronic configuration of hydrogen. How do we do that? Well, the first thing we write is the energy level. So hydrogen is in the first energy level. Then we write the shape. It's using an S-type orbital, S. Okay, and it is supposed to be a lowercase s, so S. And then there's only one electron in hydrogen, right? Hydrogen has one electron. Helium would have two, so hydrogen's only got one. So we do a superscripted 1 for the electron that's in there. So this first number tells you the energy level. That's technically called the principal quantum level. So that tells us the energy level. This next letter, the letter tells you the shape. And the exponent up top, that tells you the number of electrons in that orbital. So the energy level, the shape, and the number of electrons in that energy level. Okay. So what else can we do? Well, we can show that electron living there. So S is just a single sphere. So we can do a horizontal line. And we use half arrows to represent electrons. Okay, so hydrogen has got one electron. So we do a half arrow pointing up to represent that electron. If anybody's a fan of Watchmen, it's a graphic novel. Garth Ennis maybe wrote that or whatever. They made a movie a while ago. HBO, Damon Lindelof. Oh my God, love me some Damon Lindelof. Anything the guy does is amazing. Damon Lindelof did a post-Watchmen movie graphic novel thing on HBO the other year. It was fantastic. Anyway, if you know what Watchmen is, there's a big blue guy in there, walks around naked. His name's Dr. Manhattan. He carves this into his head when he, because he's so fond of hydrogen. Anyway, if you get the reference, great. If not, probably like, what the heck is that guy talking about? We are going to draw this. So I now want to draw, we're actually going to draw all the way up to calcium. So how would we draw this? It's very simple. S-type orbitals are spheres. So I'm going to do a dot for the nucleus. I'm going to draw a sphere, and I'm going to show one electron whirling around in that sphere. That is our drawing for hydrogen. So this is where hydrogen, its Aufbau, its electronic configuration is 1s1. It's one electron whirling around in a spherical orbital. There's a bird outside my window here, just chirping away. It's sitting on the air conditioner. All right, let's do the next element found in nature, which is helium. So here we go. We want to do helium now, folks. Helium, remember, we moved over to here. Helium lives here. So we're going to write the full electronic configuration of helium. Helium is a 1s. It's using a first energy s-type orbital. But helium now has 2 electrons. 1, 2. It's a 1s2. One of the most important things that you're going to learn tonight is that an orbital can only hold up to 2 electrons. An orbital can only hold up to 2 electrons. An orbital can only hold up to 2 electrons. So what actually happens here with helium is this s orbital is now filled. So that s orbital is boop-de-boop, completely filled. So if I want to draw, oh, and by the way, so we put the first electron in as a half arrow pointing up, and we put the second electron in as a half arrow pointing down. That's Pauli's exclusion principle. We'll get there in a moment. Don't worry about it for now. Just do. You'll pick up the pattern. It's going to be okay. I now want to draw a picture of this. I'm going to do a dot for the nucleus. Again, it's an s-type orbital, and I have 2 electrons, so half arrow up, half arrow down. That's what helium would look like. What the half arrows are meant to represent is that one electron spins one way and the other one spins the other way, kind of like clockwise and counterclockwise. That's what it's meant. We'll get to Pauli's exclusion principle and why that is in a second. So we have, ladies and gentlemen, just gone all the way up to helium. We've actually exhausted the first energy level. If you look at the first energy level, the only thing in it are the S's. There's no 1Ds and there's no 1Ps. The Ps do not exist for the first energy level. So we did hydrogen, we did helium, now we're going to do lithium. Here we go. So lithium. We always start at hydrogen. We're writing the full electronic configuration. Now you'll learn a shortcut a little later tonight called the noble gas configuration. But we always start up here and we work our way to whatever element we're trying to get to. So right now we're trying to get to lithium. So we start here. Our first orbital is a 1s orbital, and we can put 2 electrons in it. So 1s2 again, that gets us to helium. But now that 1s orbital is filled. It's got 2 electrons in it, half arrow pointing up, half arrow pointing down. We are done with the first energy level. So now we're going to drop down to the second energy level. So now for lithium, this is going to be a second energy, again, an s-type orbital, so 2s. But lithium only has 1 electron in there, 2s1, half arrow pointing up. So lithium is a 1s2, 2s1. 1s2, 2s1. 1s2, 2s1. Now I want to draw a picture of it. It's going to be pretty easy. It's going to be 2 spheres. We're going to have a first energy sphere and a second energy sphere. So let's try it. Dot for the nucleus. You've got the 1s orbital. Okay, that's got 2 electrons. The second s orbital is now on the second energy level. So it's got to be further away from the nucleus. And it's going to have 1 electron in it. We just show the 1 electron like that. Okay, and you can put it anywhere on the circle. That doesn't matter, right? You can put it over there. That's fine. So 1s2, 2s1. This is what the electron cloud for lithium would look like. Now, so far, you should be saying, wait a minute. Doesn't look like Bohr was wrong. These are just spheres. Bohr was right. I don't get the big. You're right. The Bohr model actually works pretty well all the way through beryllium. You're going to see here in a second when we get to boron, though, Bohr model falls apart immediately. Doesn't work anymore. You'll see why. Anyway, here we go. Let's do beryllium. Beryllium, going to be a 1s2. That's going to get you to helium. And then it's going to be a 2s2. 2s2. That gets us to beryllium. Now that s orbital is now filled. So the 1s has got 2 electrons. The 2s has got 2 electrons. When we go to draw the picture of this thing, we're going to do a dot. There's my 1s, 2 electrons. There's my 2s, 2 electrons. That's my drawing of beryllium. You can see the 1s is filled and the 2s is filled. We are now out of room. That 2s is done. We pause there. Any questions so far? All right, cool. Now we got to do boron, folks. And when we get to boron, something different going to happen. Boron, we always start up here if we're writing full electronic configurations. Right now, we're trying to get to boron. So it's going to be a 1s2. That fills the 1s orbital, essentially gets you to helium. Nothing left in the first energy level. Drop down to the second. 2s2, that's going to get you to beryllium. So now that 2s orbital's filled. But if you look, we still have more left in the second energy level. If you follow the second row over, there are 2 p's. So boron is our first 2p orbital. And boron is going to have only 1 electron in that 2p. Now, the 2p subshell can hold up to 1, 2, 3, 4, 5, 6. Why is that? Here's why. We're not done. Hang on. The p's come as a set of 3 orbitals. You get a vertical dumbbell, a horizontal dumbbell, and a dumbbell that goes away from you and comes out at you. Each one of these can hold 2 electrons, right? So this guy can hold 2, that guy can hold 2, and that guy can hold 2. That's a total of 6. That's where the 6 electrons come from. So what do we do here for the p's? The p's come as a set of 3 orbitals. We're going to do 3 dashed lines. And 1 electron is living there, so we do 1 half arrow pointing up in that first orbital. So here's our electronic configuration for boron. It's a 1s2, 2s2, 2p1. Again, it's a 1s2 to helium, 2s2 to beryllium, 2p1 for boron. Now we got to draw a picture. Okay, people always get all worked up about drawing the pictures. They're like, there's no way he can grade that, blah, blah, blah. This is not a skill that I ever wanted to have, but I can look at a drawing of an atom and almost immediately tell you what atom that is, and I can tell you if you messed it up somewhere. Trust me, I can grade these. Okay, so how are we going to draw this? We're going to do a dot for the nucleus. We got a 1s orbital first. So we're going to do a sphere first, and that's got 2 electrons in it. If you're the kind of person that's easily confused, cross them off as you go. That guy's now done. Now we do the 2s. So we got another sphere here, and that's got 2 electrons in it. Cross that off. The only requirement here is that the orbitals have to get bigger every time. So now we go on to the 2p. So we're going to do a vertical dumbbell, a horizontal dumbbell, and a dumbbell that's going away from you and coming out at you. Vertical dumbbell, horizontal dumbbell, and then we got a dumbbell that is in the z-axis. So it's coming out at you and it's going away from you. How do I do that? I draw under 45. I wedge the one. This is the one that's like, coming out at you. And then I dash the other one like it's going back into the board, right? So that's how I do it. I got 1 electron here, so we always just put it in this top p orbital. Let it chill right up top there. So here's our drawing for boron. Boron is a 1s2, 2s2, 2p1, pop 1 electron in that vertical p orbital. On to carbon! And carbon's where something special is going to happen called Hund's rule. So don't work ahead. Hang in there. We'll do this guy together. All right, if we're trying to get to carbon here, carbon going to be a 1s2, 2s2, that's going to get you to beryllium. And then carbon is going to be a 2p12, 2p2. And this is where you're going to have two options. One of them's right, one of them's wrong. S's come as 1, P's come as a set of 3 dumbbells. The 1s is easy, up, down. The 2s is easy, up, down. But how do you do the 2p2? You have two options. Watch, don't do. First option, you could put them together in the same orbital. Or the second option is you could spread them out, okay, and put them in one in each orbital by themselves. What do you do? The answer, the second one. And it's a pretty obvious reason why. Here's why. Electrons are negative. Confining two negative particles to the same orbital when there's space to spread them out is higher in energy, right? If I trap two negative particles in the same dumbbell lobe, they're going to interact and they're going to repel, and that's going to kick the atom into a higher energy state. It's like having a 4-bedroom house and forcing, two sisters to share a bedroom when you got an empty bedroom. You know what I mean? Like, who in their right mind? That's only going to cause problems, right? They're just going to fight. Okay? If you got the space, spread them out. Now, eventually, if you have too many electrons or too many kids, you're going to have to start doubling them up, right? Then people are going to have to start sharing. Okay? But until we get to the 4th electron in a p subshell, you don't double up. This is called Hund's rule. H-U-N-D''S. Hund's rule. And if you go to Wikipedia and you read about it, it's going to be really boring. It's going to be like the lowest energy conformation for an atom is one in which you have the most number of singly occupied electrons in degenerate orbitals, blah, blah, blah. It's very simple. If you get a set of orbitals, put one electron in each orbital before you double them up. That's Hund's rule, folks. All right. Ooh, losing my voice on a Monday. Soon I won't have to talk all day. This is my last week of township till summer. Oh, man. Can't come soon enough. Woo! All right. Where were we? We're doing nitrogen. Watch. We're kind of going. We're going to skip a little bit here, right? To try to keep it moving. Watch. We're like nitrogen. Nitrogen would be a 1s2, 2s2, 2p3, 2p3. Okay, and we got an extra electron there. Oh, we never drew carbon, did we? Let's draw nitrogen. Let's draw nitrogen here. So if we're going to draw nitrogen, we're going to do a dot for the nucleus. We've got our 1s orbital. Cross it off as you go. We've got our 2s orbital. Boop. Cross that off as you go. Now you get the sets of p's. Watch. You get a vertical p. You get a horizontal p on the y-axis, x-axis, but we live in 3 dimensions. So this is our Cartesian plane, and then we need an orbital going into your paper and coming out of your paper. Now, carbon would have been 1, 2. It was a 2p2. But nitrogen is a 2p3, so we put it over there. That's how we fill these guys up. So we always go in this direction. 1, 2, 3. Then we go back and double up. Double, double, double when you're filling the p subshell. So there's our drawing for nitrogen, folks. Drawing for nitrogen. Oxygen. Yeah, we don't have to do all these. Okay. Oxygen would be a 1s2, 2s2, 2p4. Now we would finally double that up, right? One of our p subshells is doubled. So we double that. We never put any electrons in these lower left lobes of the P's. Now, when you get to organic chemistry, you'll learn why. They're actually anti-bonding molecular orbitals. No. Or anti-bonding lobes of atomic orbitals that interact with molecular orbitals. Don't even worry about it. Don't even worry about it. Nope. They just go up here. Fluorine. Fluorine would be a 1s2, 2s2, 2p5. Now that's doubled. So there's fluorine. And then finally, neon. Neon would be a 1s2, 2s2, 2p6. And now that's doubled. There's your drawing for neon. How are we feeling? You just got through the first two energy levels. So yeah, we just did the whole second energy level. Now we're going to drop down. We're going to do sodium here, folks, which is our first one in the third energy level. Here we go. Let's do sodium together. So sodium, living down here. Let's write its electronic configuration. We always start up here. So that's a 1s2 to get you to helium. Nothing else in the first energy level. We drop down. Beryllium is going to be a 2s2. Then it's 2p6 to get to neon, 2p6. And now sodium is going to be a 3s1. 3s1. S's come as a single orbital. P's come as a set of 3. And S's come as a single orbital. Take a second and catch up. We got our 1s, our 2s, our 2p6, and then our 3s1. I, of course, want to draw the picture of this now. So let's draw a picture. We're going to do a dot for the nucleus. We've got our 1s orbital. So there's our first sphere. We got a 2s orbital. There's our next sphere. We got our 2p's. So we're going to do a dumbbell, dumbbell, dumbbell. I'm running out of room. I'm going to have to move down here soon. We got 6 electrons. 1, 2, 3, 4, 5, and 6. And then we have our 3s. So this sphere needs to be the biggest one yet. I ran out of room. It's got to be the biggest one yet. And then pop an electron out there living in that sphere. That went on there really faint for some reason. Pop an electron there living in that sphere. Right? There's your 3s1. That guy right there. Are you picking up on the pattern? 1s2, 2s2, 2p6. Sodium was a 3s1. Magnesium would be a 3s2. Magnesium, you would just pair that guy. It'd just be a 3s2. Let's jump. Let's try to go out of order here, folks. How about you try to do sulfur? Can you draw sulfur? Can you write the electronic configuration of sulfur? And then can you draw it? So we're really jumping here. We're skipping aluminum, silicon, phosphorus. Let's try. Can you predict what sulfur would be? And can you draw it? You got this, folks. All right, sulfur, folks. We got this. Sulfur is a 1s2. That gets you to helium. 2s2. That gets you to beryllium. 2p6. That gets you to neon. 3s2. That gets you to magnesium. And then sulfur is going to be a 3p, 1, 2, 3, 4. It's going to be a 3p4. Take a second, look at your configuration. Is that what you wrote? S's come as a single orbital. P's come as a set of 3 orbitals. S's come as a single orbital. P's come as a set of 3 orbitals. I got 4 electrons. Up, 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 and a down. Now we got to draw this thing. Okay, how do we draw it? Oh boy, I'm going to try to draw it here. Let's see how this works. Dot for the nucleus. We got a 1s orbital. There's my 1s. We got a 2s orbital. There's my 2s. We got a set of 2p's. We got a vertical dumbbell, a horizontal dumbbell, a dumbbell going away from you and coming out at you. That's got 6 electrons living in it. So there's that guy. A 3s, so that's a sphere. That's got 2 electrons living in it. And now we got a 3p. We need to do another dumbbell. We got a vertical dumbbell, a horizontal dumbbell, and a dumbbell going away from us and coming out at us. It's got 4 electrons. 1, 2, 3, and 4. There it is. That is our drawing for sulfur. Pretty crazy. I know. Chlorine would just be a 3p5, 1s2, 2s2, 2p6, 3s2, 3p5. And then argon would be a 1s2, 2s2, 2p6, 3s2, 3p6. 3p6. The largest elements that we are going to write electronic configurations for and draw, we're going to write electronic configurations all the way down to barium, but the largest ones I'm going to make you draw are going to be potassium and calcium. So why don't y'all do potassium? Let's write the electronic configuration of potassium, and let's draw potassium. You got this. It's getting messy here. You can do this. Let's do potassium. Write the full electronic configuration of potassium, letter K. Does it matter where the P's overlap? I don't know if I follow the question. You mean when you're drawing, Bree? Like in the drawing?
Yeah, like if you like when you're drawing it and you do the bigger P, does it matter? Like if they're just like you
No, the
draw it
only
a little bit bigger than
requirement,
the other.
yeah, that's fine. The requirement is that each new orbital you draw must go further away from the nucleus than the previous, right? So, like, for example, so if here's my 1s, and then a 2s, and then here's my 2p, and then here's the 3s. Now, if I'm going to draw the 3p, I draw it still vertical. So it's bigger than those 2p's, right? It's bigger now. And then, there's my 3p and the other. So now it's just as long as it's further outside. That's all.
Okay, thank you.
You got it. I'm going to try to switch markers here back to a black marker. Maybe it'll show up better. Potassium, guys. Give potassium a shot. Element K. All right. Potassium. Potassium is going to be a 1s2, then a 2s2. That gets you to beryllium. Then a 2p6, that gets you to neon. Then a 3s2, that gets you to magnesium. Then a 3p6, that gets you to argon. And then potassium is going to be a 4s1. 4s1. S's come as a single orbital. P's come as a set of 3. S's come as a single orbital. When you go to draw it, again, potassium and calcium are going to be the biggest ones you have to draw. When you go to draw it, dot for the nucleus. There's my 1s. There's my 2s. Cross them off as you go. Then you have the 2p. Then you got the 3s. So we're drawing a sphere. Then you got the 3p. That's got 6 electrons. 1, 2, 3, 4, 5, 6. And then we got the 4s1. There's your 4s1. So 1s2, 2s2, 2p6. People always say, how could you possibly grade that? Right? It's not that bad. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. It's not that bad to grade. Calcium would just be a 4s2, and you would pair that electron. Calcium is that calcium when we get to periodic trends on Wednesday. Calcium is actually a little bit smaller than potassium, believe it or not. It's got an extra proton, sucks it in tighter. Anyway, how are we feeling with the writing of the configurations and the drawing? People do sometimes complain about the drawing, and I say, you know what? I mean, if you can write electronic configurations, but you can't draw a picture and tell me what it means, why the heck are we writing electronic configurations, right? The whole point of these electronic configurations is to tell you what the electron cloud looks like. And if you can't convert this into a picture of what it looks like, you're wasting everybody's time, right? I mean, the drawings, I think, are more important, right? Because this is what, when now we did calcium, this is now calcium. This is what calcium's electron cloud looks like, right? It's a sphere and another sphere and some dumbbells and a sphere and some dumbbells and finally a sphere in what it's called its valence shell, its outer shell. So, yeah. Exciting
I,
stuff. Go
I
ahead.
do have a question actually.
Yeah.
So earlier you said that like with the drawings, you said that like all that matters is that each orbital gets bigger. But I thought before you said that they would I guess like get bigger as you go down because it's like a bigger energy jump. So am I understanding that like incorrectly? Like these two aren't.
So what happens? The orbitals get. I think here's what you're conflating. The orbitals have to get further from the nucleus, right? But they actually start to get closer together. Now, I don't need, as you get further out, now I don't need you to go into that level of detail, but here's what I mean by that. If we were going to draw this, and again, I do not need that level of detail, okay, but hang in there. Here's what would happen. Here's my 1s orbital. The biggest gap in your drawing, and again, please don't actually do this. But if you were going to do this, the biggest gap should be here. Okay, because the orbitals get closer together. Whenever I add a new orbital, it needs to be closer to this one than this one was to this one. So you'd have a big gap between the first and second. Then when you do the the two P's should be closer than this guy is, right? So see how that's closer than this, right? So that's really what I was talking about there. And then that 3s should be closer yet. All right, so that gap, what happens as you get further out from the nucleus, the orbitals start getting closer together. Like they start to almost stack, and then you get what is that called? It is called, oh my goodness, a convergence limit. That almost slipped my mind. I'm getting old. Okay, it's called a convergence limit, where eventually the orbitals just become one, and that's where ionization occurs. So, is that what you were talking about, Savannah? Is that what?
Yeah, no, that makes a lot more sense to me
I
now.
totally don't. I do not want you to try to draw that, okay? Because your drawings are going to get outrageous. So don't worry about that aspect. You're just trying to get the right, So a dot from the nucleus. Okay, sphere, another sphere. Don't try to space them, right? Then a set of dumbbells, right? Then another sphere, and don't worry about spacing them. As long as each new orbital you draw is further out than the previous one, that's what we're going for with this. Cool. That's a good question. Good question. Okay, let me fix my periodic table back up here. Right, it got a little messy there. All right, so we made it to calcium. So here's the good news. That's the biggest atom that you're going to have to draw configurations for. Let me re-Aufbau my periodic table. I move helium over here. Label my blocks. And I number my rows. That is something you want to practice, folks, because for the second exam, you're just getting a periodic table. So you want to practice being able to mark it up like I just did, right? So as if you're always doing your homework, and you're always doing the problems, and the periodic table is already marked up. Then you get to the exam, and it's like, uh-oh, I forget what I had to do. So actually practice taking a fresh periodic table and getting it ready to Aufbau. You want to practice that as a skill. Okay, here we go, folks. All right. The D's. We got up to calcium. Why do we stop drawing at calcium? Because after calcium, we hit the D's, and I ain't going to make you draw those. Now, if you take college chem, they might, like, no, I mean, by college, I mean, like graduate school chem or inorganic chemistry. Like, if you take the next, so usually it's like Gen Chem, Organic Chem, and then Inorganic Chem. If you're a Chem major, you take Inorganic Chem, you're going to have to memorize those d orbitals, okay? But not right now, okay? So we're not going to draw past calcium, but we're going to write electronic configurations past calcium. And the first thing that makes the Ds a little different than the S's or P's is that the Ds are in one energy level less than the row they're in. So these are not the 4 Ds. These are the 3 Ds. So a lot of people like to write a 3 here between calcium and scandium, okay, to show, hey, remember, dummy, this is the 3rd energy level. And then a lot of people like to write a 4 here between scandium and yttrium to say, hey, buddy, when you get into here, these are the 4 Ds. So let's say I wanted to write the full electronic configuration of scandium. So scandium going to be a 1s2 that gets you to helium, 2s2 that gets you to beryllium, 2p6 that gets you to neon, 3s2 that gets you to magnesium, 3p6 that gets you to argon, 4s2 that gets you to calcium, 4s2, and then it's a 3d1. 3d1. Now, we can't draw it, but we can do the lines and half arrows. So S's come as a single orbital, that's a single line. S's come as a single orbital, P's come as a set of 3 orbitals. S's come as a single orbital, P's come as a set of 3 orbitals. That 4s comes as 1 orbital. So this gets me up to here, 4s2. Now we have the 3d1. D's come as a set of 5. Hopefully you see a pattern. S's come as 1 orbital. P's come as 3 orbitals. D's come as 5. The F's will come as 7. Okay, so you add 2 orbitals each time. Okay, so the D's come as 5. So it's 1, 2, 3, 4. Oops. 4 and 5, and there's 1 electron to show it there. The d orbitals are going to exhibit Hund's rule again. So the d orbital is like we're going to half fill the d subshell, and then we're going to go back and we're going to double up. So why don't we try, oh man, I don't know. Why don't y'all try nickel? Nickel. Give me the full electronic configuration of nickel. And try to do the lines and half arrows and all that stuff. Nickel, right here, element 28. You got this, folks. All right. Nickel. Nickel going to be a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, and then nickel going to be a 1, 2, 3, 4, 5, 6, 7, 8, 3d8. S's come as 1 line. P's come as a set of 3. S's come as 1. P's come as a set of 3. S's come as 1. D's come as a set of 5. 1, 2, 3, 4, and 5. We go Hund's ruled it. We got 8 electrons. 1, 2, 3, 4, 5. Now we go back 6, 7, 8. That's your electronic configuration with lines and half arrows for nickel. Again, what is the whole point of this? This is Aufbau. This is to teach you how to build the electron cloud. If you wanted to build the electron cloud for nickel, this is what it would look like. It would be sphere, sphere, dumbbells, sphere, dumbbells, sphere. Crazy looking D things, okay, with 8 electrons in it. The D's can hold up to 10, folks. Zinc, because think about it, if you got 5 orbitals, and each orbital can hold up to 2 electrons, 5 times 2 is 10. The D's can hold up to 10. So zinc would be a 3d10. Chow, ka-chow. Now that's filled. Once you get past zinc, here's the thing you got to remember. You are back to the 4th energy level. Only the D's are 1 energy level less than the row they're in. These are the 4 S's. These are the 4 P's. So you're back up to the 4th energy level there. Once you get out of past the D's. So for example, I don't need lines and half arrows there. Let's, it's kind of starting to get a little crazy. I know what you're thinking. You're saying, Nate, isn't there a shortcut? There is. I'm not going to teach you that shortcut till we get to barium. Okay, but there is a shortcut. These can get a little bit shorter. If I wanted to do arsenic, for example, follow me. Arsenic would be a 1s2, 2s2, 2p6, 3s2 to magnesium, 3p6 to argon, 4s2 to calcium, 3d10 to zinc, and then a 4p3 to arsenic. And again, everything's going to be filled except for that P, that last P subshell, that would be half filled like that. Okay? You can see hopefully the pattern, right? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2 would get you to barium, right? Hopefully you're picking up on the pattern. I want to do one more element before barium, then we'll do barium, and then I'll teach you the shortcut. So, man, I don't know. Let's do, oh my goodness. Let's do tin. I would like you guys, and again, please don't do the lines and half arrows. That's just going to be so messy. I would like you to do tin, which is from the Latin stannum, element 50, please. Please write the full electronic configuration of tin. Go ahead. All right. Tin. Element 50. Here we go. It's going to be a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. That gets us to zinc. Then it's a 4p6 to krypton. Then it's a 5s2 to strontium. Then it's a 4d10 to cadmium. 4d10. And then it's a 5p2 to tin. There it is, folks. That's tin. Any questions so far? All right, the moment you've all been waiting for. We are going to write the full electronic configuration of barium. I want you to give it a shot. Cesium and barium, largest elements we're going to do. Okay, so I want you to write the full electronic configuration for barium, element 56. You got this. By the way, what do you do with a dead chemist? Barium. Tell you another chemistry joke, but all the good ones. Argon. You'll get it later, don't worry. Anyway, barium, folks. Go ahead and write the full electronic configuration of barium. If you can do this, you're good to go. With these electronic configurations, at least the full ones, then we'll teach you the shortcut. All right, folks. All the way to barium. 1s2, 2s2, 2p6, 3s2, 3p6. Let's regroup. 1s2, 2s2, 2p6, 3s2, 3p6. We're up to argon. Now I'm starting here at potassium. So 4s2 to calcium, 3d10 to zinc, 4p6 to krypton, 5s2 to strontium, 4d10 gets us to cadmium. Then it's a 5p6 to xenon. And then finally, we drop down 6s2 gets us to barium. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. So that's the largest Aufbau we'll ever do. That's the largest full electronic configuration.